Good morning, this is Math 145, day 8. And today I thought to start with a recap. That is the picture of a chunk of the cosine graph in blue, and then the graph of the inverse, that's red. And the point is that they're mirror images. And we pick a chunk which is chosen so that it passes the horizontal line test. It does so because it's decreasing. No horizontal line can intersect this blue piece of the cosine graph twice, only once. And now we're going to play the same game with the sine, just so you've seen that once in your life. Here's the graph of the sine function. Then we pick a piece of it. And it's convenient to go from negative pi over 2 to positive pi over 2. Again, it's passing the horizontal line test because no horizontal line can intersect that twice because it's increasing. And then we plot the graph of the arcsin function. In red, and they're mirror images. If you ever want value, we can actually read that off the red graph. For example, arcsin of 0 is 0, arcsin of 1 is pi over 2, arcsin of negative 1 is negative pi over 2, but you can also just read it off the graph of the original sine function. Because the sine of pi over 2 is 1, the arcsine of 1 is pi over 2. It goes flip, flop, teeter, totter. That's how inverses work. So we'll leave it at that and go back to do some more work with paper and pencil. So we want to investigate relationships between, well, sine and arcsine. So to begin with, sine of arcsine of x is x. This is how inverses are supposed to work. You concatenate them or form the composite, and you get the identity function. However, this is only for legal input values for the arcsine function. So for -1 less or equal x less or equal 1. If you try to choose x equal to 2 here, then you get an error. Arcsine of 2 is not defined. But it's a great exam problem to ask about sine of arcsine of 0.369, and that is 0.369. You don't need to whip out a calculator, it's just going to be that same number. And to record this, sine of arcsine of 2 does not exist. DNE. Now let's try this the other way around. We had sine of arcsine, deserves to be boxed. And now arcsine of sine of x. This is also x, as long as we are in that particular special interval where we define the inverse. So this is true for all x in negative pi over 2 to pi over 2. Works great there. And this time we can actually substitute any x value that we like, because sine x doesn't have a problem with that. It gives us a value between -1 and 1, and arcsin is defined for those values. So there will always be an answer. It just won't be x when we're outside of this interval. So let's investigate. Begin with arcsin of sine of 0.368, because it's different, is that same number, 0.368, because that is in the special interval. But arcsin of sine of, let's say, 5 pi over 3. We actually have to work this out. This is the arcsin of, what's sine of 5 pi over 3? One of the nice angles. This is 6 degrees less than a full turn, so it is -1/2 square root 3. And that is negative pi over 3. What's going on here? Look at these angles in a diagram with a unit circle. So the 5 pi over 3 is about here. It goes all the way around like that, counterclockwise by default. And negative pi over 3 is this angle, clockwise, because it's negative. Write that in. Negative pi over 3. So this is an angle in the interval we are looking at, which is between negative pi over 2 and positive pi over 2, that has the same sine value. And that is what we get from substituting 5 pi over 3 into this composite function. We get back an angle in our special interval which has the same sine value. One more example. Arcsin of sine of 4 pi over 3 turns out it's the same thing. -1/2 square root 3. Oops, that was supposed to be arcsin. And that is negative pi over 3. So what is the geometric situation here? Four pi over 3, that is down to here. Angle like this on the unit circle. Gets us to this point. And again, we're looking for an angle between negative pi over 2 and positive pi over 2. So that's the right half of the unit circle, which has the same sine value. And that's going to be over here. And that's why we get the same answer. Or pi over 3, and this guy here is negative pi over 3. Generally, if your angle is in the left half of your unit circle, you flip it about the y-axis to the right half, and then you're good. If you're already in the right half, then you get that same angle back. Except if your angle is bigger than 2 pi, then subtract 2 pi. So there's a third possibility that can happen. Arcsin of 2 pi plus pi over 4. Let's do it this way. And you just say, okay, subtract those 2 pi. Because the sine has period 2 pi. And then we're in the interval where we want to be, where it works, just without any further complications, and we get pi over 4 as the answer. All of these denominators are supposed to be 4 in this example. Okay, so it's best not to try to remember every single detail here, but to remember the principle. And when you get an actual problem, then develop this as much as you need from first principles. What is an inverse supposed to do? What is the domain for the sine function that we need so that the inverse is defined? Or what's the domain for the arcsine function, -1 to 1? What's the range? What does this look like on a unit circle? And then you solve those problems. Don't just load up your memory with all 6 trig functions and their inverses. I think if you understand the principle really well, that is more valuable than all those details. One more thing from lesson 7. And that is the cosine of arcsine of x. What is that? Cosine of arcsine of x. And to investigate what's going on here, let's give this thing a name. Let's say A is the arcsine of x. Therefore, sine of A is x. If we're in the right interval, let's not worry about that for the moment. If A is in the right interval and x has to be between -1 and 1 and so on. Okay, so what that formula up there said is the cosine of A. What is that? And then we can apply Pythagoras. Cosine of A is plus or minus the square root of 1 minus sine of A squared. And the sine of a, that was x. So this is plus minus square root of 1 minus x squared. Isn't that amazing? We have calculated cosine of arcsine of x. And we come up with a function that is perfectly well known. No need for any of those fancy new function buttons on your calculator if you have a square root button. So that's a surprising connection between those inverse trig functions and the original trig functions. Again, probably best not to remember the details and rediscover that when you need it, but keep in mind there is that thing out there with the square root and Pythagoras. What about the plus or minus sign? Can we figure that out real quick? The range of the arcsine function is between negative pi over 2 and pi over 2. The cosine is never negative in that interval. And therefore, we can rest assured in that plus minus equality up there, we actually always get the plus sign. Always the plus sign, but the whole thing is only legal for x between negative 1 and 1, of course. All right, a similar thing can be done with sine of arc cosine of x, and can also be done with arc sine of cosine of x. But all of this is the same ideas every time. You always get this kind of a Pythagoras deal with the square root. So the book has more worked examples, and this should be enough for a video. And we go to lesson 8.